Diving into gravitons today.
Mm.
It's mind-boggling stuff, really. You've sent in some pretty fascinating stuff about this, and I'm really excited to kind of unravel this whole mystery with you. I mean, we all know that, like, gravity is what keeps our feet on the ground, right?
Mm-hmm.
But what actually is it? At the smallest level, physicists think that there might be these particles called gravitons, and these gravitons might actually carry the force of
It's
gravity.
like a cosmic game of catch.
Yeah.
But the thing is, well, this is where Betteridge's law of headlines comes in, like that thing that says any headline that ends in a question mark can be answered with no.
Right.
Well, are gravitons real?
Mhm.
Proving their existence is a challenge. It's a big challenge.
It really is, yeah. It's
Yeah.
like trying to find a single grain of sand in the Sahara Desert.
Yeah.
But, I mean, let's just back up a little bit. What exactly are gravitons, and why are they so important to physicists?
Okay, so imagine this. Just like photons are particles of light, right? Gravitons are thought to be particles, but they carry the force of gravity. This comes from quantum field theory. It's been very successful, quantum field theory, in explaining other fundamental forces, like electromagnetism, for example. And each of those forces has a force-carrying particle.
Right.
So this stands to reason that gravity might too.
So it's like this pattern in the universe.
Yeah.
And gravitons would be the missing piece.
Exactly.
But, I mean, if it's so consistent, why haven't we found them already?
Well, because gravity is incredibly weak compared to other forces. Like, we're talking 10 to the power of 40 times weaker than electromagnetism.
Yeah.
Like, trying to detect a graviton is like trying to hear a butterfly flapping its wings in the middle of a hurricane.
Oh, wow. That's an incredible image.
Yeah,
So even if gravitons are everywhere, they're almost impossible to detect,
exactly.
like directly.
Exactly. On a subatomic level, right, where quantum mechanics reigns, the other forces just completely drown out any gravitational effects. And when we look at larger objects, like planets and stars, we're no longer in the quantum realm. So our observations are governed by Einstein's relativity, not quantum gravity, which is where gravitons would come into play.
Okay, so it's like we're stuck between two worlds.
Yes.
I mean, we need quantum gravity to describe gravity at the smallest scales,
Mm-hmm.
but that's where it's the hardest to study.
Precisely. And that's why the search for gravitons is so compelling. It's pushing the boundaries, of our understanding of the universe. But we're not starting from scratch. We have some ideas about what gravitons might be like based on, how gravity behaves.
Right, okay. So let's, like, play a little guessing game.
Okay.
Based on what we know about gravity, what would gravitons be like if we could, like, actually hold them in our hands?
Okay, so let's break it down. First of all, gravity acts over vast distances, like across galaxies, right? So gravitons would have to be massless, just like light.
Yeah.
Second, gravity affects everything, whether it has an electric charge or not,
Right.
which means gravitons would be electrically neutral. And finally, based on the way that gravity acts as an attractive force, physicists think that they would have a spin of 2.
A spin of 2.
Now, spin is kind of a tricky concept, but think of it as like a particle's intrinsic angular momentum.
Okay.
And a spin of 2 specifically relates to how gravity warps spacetime.
Wow. So we're talking about these tiny, massless, neutral particles with a specific spin.
Yep.
Just zipping around, holding the universe together.
Yeah.
I'm starting to see why physicists are so obsessed with finding them.
Yeah, it's a pretty tantalizing idea.
You do.
These tiny messengers weaving the fabric of reality. But as we've discussed, finding them is going to be incredibly challenging.
Yeah. Well, you've piqued my curiosity even more.
Good.
So if detecting individual gravitons is practically impossible right now, how are scientists even, like, approaching this problem?
That's where things get really ingenious. Scientists are looking for indirect ways to observe the effects of gravitons. It's like trying to study the wind, You can't see the air itself, but you can see the leaves rustling or flags waving.
So we're looking for the rustling leaves of gravitons.
Yeah, something like that.
Okay.
Interesting. One of the most promising avenues involves these things called gravitational waves.
Okay.
They're these ripples in space-time. They're generated by incredibly massive objects like black holes
Right.
or neutron stars when they collide or spiral into each other.
I've heard about gravitational waves.
Yes.
Didn't scientists actually detect them for the first time relatively recently?
Yes, they did.
Like confirming Einstein's predictions?
You're absolutely right. The detection of gravitational waves was a monumental achievement. But here's where it gets even more exciting. Some theories suggest that these gravitational waves might be quantized.
Quantized?
In other words, they might exist in like discrete packets of energy, much like light exists as photons.
Wait a minute. Are you suggesting that those packets of energy in gravitational waves could be gravitons?
Exactly.
Hmm.
If we could find evidence of this granular structure in gravitational waves, it would really support the idea that gravity is indeed quantized, that gravitons are the fundamental building blocks of those waves.
So it's like looking for a grainy texture in the fabric of space-time itself.
Yes, that's a great way to put it. Instead of trying to capture a single graviton, we're looking for the collective fingerprint
Right.
that they leave on these cosmic ripples.
Okay, that makes sense. But how do we even detect gravitational waves in the first place? I mean, space-time isn't something we can just, like, grab and measure, is it?
No, it's not, but we have these incredible instruments called gravitational wave detectors.
Right.
The most famous ones are LIGO and Virgo.
Okay.
They use lasers and mirrors to measure incredibly tiny distortions in space-time caused by passing gravitational waves.
So we're talking about lasers bouncing back and forth, and if a gravitational wave passes through, it, like, changes the distance that those beams travel.
That's the basic idea, but we're talking about mind-bogglingly tiny changes, like, a fraction of the width of a proton.
Wow.
But these detectors are so sensitive, they can pick up these subtle variations.
It's amazing what science can do. But has LIGO or Virgo given us any hints about this, grainy structure in gravitational waves?
Yeah.
Are we any closer to finding those gravitons?
Well, it's still early days. We've detected plenty of gravitational waves, which is incredible in itself.
Yeah.
But so far, no definitive evidence of quantization. But that doesn't mean it's not there. We might just need even more sensitive instruments.
Right.
Or more clever analysis techniques.
So the search continues.
Yes, it does.
I love how this is pushing the limits, of our technology and understanding. But what if, and this is a big what if, we never find definitive proof?
Yeah.
Does that mean the idea of gravitons is just like a dead end?
Not at all. The beauty of science is that even if we don't get the answer we expect, the journey is incredibly valuable. We're learning so much about the universe in the process. And remember, we're trying to solve one of the biggest mysteries in physics, unifying gravity with quantum mechanics.
Right. So even if gravitons turn out to be like a theoretical mirage, the search itself is pushing us towards a more complete understanding of the universe.
Absolutely. But let's not lose hope just yet. Imagine if we did find those telltale signs of gravitons.
Yeah.
It wouldn't just confirm their existence, it would be a paradigm shift in physics.
Wow.
It would mean that all four fundamental forces, the strong force, the weak force, electromagnetism, and gravity, are all governed by the same quantum principles.
A unified theory of everything.
Exactly.
It's like finding the Rosetta Stone for the universe.
It is, yeah.
But, I mean, haven't there been other attempts to unify gravity with quantum mechanics?
Right.
Where do gravitons fit into the bigger picture?
Yeah, you're right. There are other approaches, like string theory and loop quantum gravity, each with its own way of reconciling these two fundamental frameworks. And interestingly, gravitons play a role in these theories too.
Oh, okay.
In string theory, for example, gravitons are thought to be excitations of tiny vibrating strings. And in loop quantum gravity, they emerge from the quantum properties of space itself.
So it's like gravitons are a common thread,
Yes.
running through many of these attempts to understand the universe at its deepest level.
Exactly. It's like we're seeing gravitons from different angles, and each perspective adds another piece to the puzzle.
Well, you've certainly painted a vivid picture of the theoretical landscape. But I'm curious to explore, some of the specific implications of gravitons.
Yes.
For instance, how would their existence affect our understanding of, like, those cosmic enigmas, black holes?
Black holes.
Yeah.
Those are a perfect example of where things get really weird and wonderful when we start talking about gravitons. But you know what? I think that's a topic best saved for our next segment.
All right, listeners, you heard it here first. We're about to plunge headfirst into the mysteries of black holes with gravitons as our guides. Buckle up. It's about to get cosmically interesting.
Welcome back, everyone. So we're about to venture into a realm where gravity reigns supreme, the mysterious world of black holes.
Oh, it's exciting.
And you know what? Our tiny friends, the gravitons, they might just hold the key to unlocking some of their secrets.
I am all ears. Okay. So we've established that black holes are these incredibly dense objects formed from collapsed stars with gravity so strong that not even light can escape.
That's right.
But how do gravitons fit into this picture? If nothing can escape a black hole, shouldn't that include gravitons too?
That's a great question, and it highlights a key difference between classical physics and the quantum world.
Okay.
Classically, you'd be absolutely right. Nothing escapes a black hole's grasp.
Right.
But when we bring quantum mechanics into the mix,
Okay.
things get a bit more interesting.
Oh, I'm sensing a but coming. Does quantum mechanics throw a wrench into the whole nothing escapes idea?
It does indeed. One of the key insights of quantum mechanics is the existence of these things called virtual particles.
Okay.
Now, these aren't particles in the traditional sense. Think of them more like fleeting fluctuations in the quantum fields that permeate all of space-time.
Right.
They pop in and out of existence constantly, usually annihilating each other almost as soon as they appear.
Okay. Virtual particles popping in and out of existence.
Yeah.
I'm trying to picture this, but how do they relate to black holes, especially in the context of gravitons?
Well, imagine this. A pair of virtual particles, let's say a graviton, and its anti-graviton,
Okay.
pops into existence near a black hole's event horizon.
Right.
That boundary beyond which nothing can return.
Right.
Now, normally, these particles would annihilate each other almost immediately.
Okay.
But because of the black hole's intense gravity, something extraordinary can happen.
I'm on the edge of my seat. Was this extraordinary event?
One of the virtual particles might get pulled into the black hole, while the other manages to escape.
What?
And the particle that escapes becomes real, carrying away a tiny bit of the black hole's energy.
Wait, are you telling me that black holes can actually leak particles even though nothing can supposedly escape? I mean, didn't we just say that nothing, not even light, can get out?
We did. But this is where the mind-bending nature of quantum mechanics comes in.
Okay.
This process is called Hawking radiation,
Okay.
named after the brilliant physicist Stephen Hawking,
Right.
who first proposed it. And this radiation, according to the theory, includes all sorts of particles,
Yeah.
including photons and, you guessed it, gravitons.
So black holes, these cosmic vacuum cleaners, are actually slowly evaporating away
Yeah.
due to this quantum quirk. And gravitons are part of that escaping energy. This is wild.
It is pretty wild, isn't it? Now, to be fair, it would take an insanely long time for a black hole to completely evaporate
Sure.
through Hawking radiation.
Right.
But the implications are profound.
Okay, so this brings up another question that's been bugging me.
Okay.
We talked about how information might be encoded in gravitons.
Right.
But isn't it said that information is destroyed when it falls into a black hole?
Yeah, that's the heart of what's known as the black hole information paradox.
Okay.
It's one of the biggest unsolved mysteries in physics.
Really?
You see, quantum mechanics tells us that information cannot be destroyed.
Right.
It might get scrambled or spread out, but it's always conserved.
Right.
But the classical picture of black holes seems to contradict this. Whatever
Oh.
falls in is gone forever, right?
Right, yeah. So we have these two fundamental principles.
Yeah.
Conservation of information from quantum mechanics and the point of no return nature of black holes from general relativity,
Right.
seemingly at odds with each other.
Right.
So how do we reconcile this?
That's the million-dollar question.
Yeah.
If gravitons are escaping black holes through Hawking radiation, are they carrying away bits of information about what's inside? Or is there some other mechanism at play that we haven't even considered? Physicists are still grappling with these questions.
So the mystery deepens. Are there any leading theories about how information might be preserved even in the face of a black hole's seemingly insatiable appetite?
There's some fascinating ideas out there.
Okay.
Some physicists believe that information might be encoded in subtle correlations
Okay.
within the Hawking radiation itself.
Okay.
Others propose that black holes might have hair?
Hair?
Quantum properties that store information on their surfaces?
Black holes with hair. I'm trying to visualize that.
It's a metaphorical term, of course.
Okay.
Hair, in this context, refers to any feature
Gotcha.
beyond a black hole's mass, charge, and spin
Right.
that would allow it to retain information. And the idea of black holes having hair is a hot topic in theoretical physics.
Okay, so by studying the properties of gravitons and Hawking radiation, or searching for signs of black hole hair, we might gain insights into this fundamental question of information conservation.
Exactly. The study of gravitons has opened up entirely new avenues of exploration when it comes to understanding black holes. And who knows what other incredible discoveries await us as we delve deeper into these cosmic enigmas.
This is also mind-boggling. We've gone from tiny particles holding galaxies together
Right.
to black holes leaking information.
Yeah.
What other cosmic wonders can gravitons help us understand?
Well, believe it or not, the implications of gravitons extend far beyond black holes. They might even hold clues about the very origin and evolution of the universe itself.
Wow.
But that's a story for our final segment.
All right, listeners, get ready for the grand finale. We're about to journey back to the dawn of time and explore how gravitons might help us unravel the secrets of the cosmos on the grandest scale. Stay tuned.
Welcome back, deep divers. So, we've explored the potential role of gravitons in holding galaxies together and even escaping from black holes. But now, get this. We're going to zoom out to the biggest picture imaginable, like the universe itself. Believe it or not, those tiny gravitons, right? They might just have something to say about how it all began and where it's headed.
Okay, I am intrigued. We've talked about gravitons as messengers of gravity, even escaping from black holes. But how could they possibly hold clues about the entire universe? Like its origin and its evolution? It seems like a huge leap.
Well, remember our discussion about quantum fields. Everything, particles to forces, it all arises from these underlying fields, right? And they permeate all of space-time. And physicists believe that gravity, just like the other forces, has its own corresponding quantum field. It's the gravitational field.
Okay, so gravitons are like the ripples in this gravitational field,
Yeah.
just like photons are ripples in the electromagnetic field.
Exactly. And here's where things get truly cosmic. So if gravitons are the quanta of the gravitational field, it means that the very fabric of space-time, right, the stage upon which the universe plays out, is ultimately a quantum phenomenon.
Hold on. Are you saying that space and time, the very foundations of our reality, are actually grainy and like quantized at the most fundamental level? Like, is there a smallest possible unit of space or time? I mean, that's a pretty radical concept.
It is. And it leads to some mind-blowing possibilities. So if space-time is quantized, it might mean that there are limits to how smoothly objects can move, or that time itself might not flow as continuously as we perceive it. It's like imagining the universe as a digital image, made up of tiny, discrete pixels, rather than a smooth, continuous canvas.
So our everyday experience of space and time is smooth and flowing. It could just be a sort of zoomed out illusion of what's happening at the quantum level. It's like we're seeing the forest, but not the individual trees.
That's a great analogy. Just like the smooth surface of a lake, right, is made up of countless jostling water molecules. Our seemingly continuous reality might arise from the underlying quantum nature of the gravitational field, with gravitons playing a key role.
Okay, my brain is officially doing somersaults. But let's get back to the big picture. You mentioned that gravitons might hold clues about the origin of the universe. How is that even possible?
Okay, so imagine the very early universe, right? Just moments after the Big Bang, everything was incredibly hot, dense, like a cauldron of energy and particles. Now, if gravitons existed back then, they would have been a part of that primordial soup, interacting with everything else.
So are you saying the gravitons for the Big Bang could have left behind like some kind of imprint on the universe as it expanded and cooled, like a cosmic fingerprint?
That's exactly what some physicists believe. They think that those primordial gravitons might have left subtle patterns in the cosmic microwave background radiation, which is the afterglow of the Big Bang itself.
Wait, so we're talking about like cosmic fossils from the dawn of time. Gravitons from the Big Bang could still be out there, leaving their mark on the universe's baby picture.
Yeah, that's the idea. Detecting these patterns would be like peering back in time, to the earliest moments of the universe, providing a glimpse into the conditions that prevailed when gravity itself was taking shape.
This is incredible. We've gone from tiny particles holding galaxies together to black holes leaking information, and now cosmic time travel. Gravitons are like the ultimate multitaskers of the universe.
It is a testament to their potential importance in the grand scheme of things, and it highlights why the search for these elusive particles is so captivating. It's a quest that really spans the smallest scales of quantum mechanics to the vast reaches of the cosmos, with profound implications for our understanding of the universe at every level.
Well, we've covered an incredible amount of ground in this deep dive. We've explored the theoretical underpinnings of gravitons, their potential role in black holes, and even cosmology. But we've also, we've touched on some pretty profound questions, really, about the nature of space and time, the origin of the universe. It's clear that the hunt for gravitons, it's more than just a search for another particle, It's a journey into the deepest mysteries of existence.
I couldn't have put it better myself. The pursuit of knowledge, especially in a field as mind-boggling as physics, is an adventure. Whether we definitively find gravitons or not, the journey will undoubtedly lead to incredible discoveries and a deeper appreciation, I think, for the wonders of the universe.
So, to our listeners out there, keep those minds curious and those imaginations open. The universe is full of mysteries waiting to be explored, and who knows, maybe someday we'll have definitive proof of those elusive gravitons, unlocking even more secrets of the cosmos. Until then, happy deep diving.